Quick confession, my bathroom scale reads 2 pounds heavy every single morning. I've made peace with it. Whatever it says, the real number is 2 pounds less. But here's the thing, stepping on it 10 more times won't fix that. It isn't noisy. It's wrong in the same direction every time.
And that is a perfect picture of the one idea behind today. A scale that's always 2 pounds high is biased. It leans the same way no matter how much data you pile up. Now picture a different cheap scale. It jitters, a pound high, then a pound low, all over the place, but averaged over many weigh-ins, it's dead on. That one's noisy but unbiased, no systematic lean.
So this is a short supplement, lecture 14.5, Estimators and Bias. It's the idea sitting underneath the confidence intervals from lecture 14. What makes a guessing recipe a good one? Let's unpack it.
Let's name the players. There is some number about a whole population you can't see directly. Call it theta. Maybe it's the population mean mu, maybe a proportion p, and all you've got is a sample.
So an estimator is the recipe, the rule you run on your sample to guess theta. And because the sample is random, the estimator is itself a random variable. Different sample, different output.
And the one demand we make of it, as the sample grows, it should home in on the truth. The estimator of theta marches toward theta as m, the sample size, gets large.
Keep the two roles straight. Theta, the parameter, is a fixed unknown number about the whole population. Big theta, the estimator, is the recipe we run on a sample. The classic example, x bar, the sample mean, is the recipe that targets mu. There's a subtlety in that word estimator worth slowing down on. It has two faces.
Right. Before you collect data, the estimator is that random rule, a whole distribution of possible answers, depending on which sample you happen to draw.
Then you actually collect the sample, plug the numbers in, and out comes a single value, theta hat. That number is the estimate. Estimator is the rule, estimate is the one number it gives you. Draw a fresh sample, you get a fresh estimate.
And here's why that matters. Look at the table. The true mean is 4. Take the sample 2, 5, 11. The sample mean is 6. The median is 5. The median's closer. But take 2, 6, 7. Now the mean is 5. The median is 6. The mean wins. Two recipes, and which one lands closer flips with the sample. So we can't judge an estimator on one lucky draw. We need a standard that holds on average.
And that standard is unbiasedness. The definition is clean. An estimator is unbiased if its expected value equals the parameter. E of big theta equals theta.
Unpack expected value for me here.
Average it over every sample you could have drawn. If those estimates pile up centered exactly on theta, no systematic lean, it's unbiased. It's the noisy but centered scale.
And the picture on the right nails it. The line curve is an unbiased estimator. Its whole sampling distribution sits right over theta. The blue one is biased, same kind of spread, but shoved off to one side.
And that gap from theta to the center of the curve has a name, the bias. It's E of big theta minus theta. Unbiased just means that gap is 0. The 2 pound scale has a bias of 2 pounds. A good scale has a bias of 0.
Let's prove the headline case. The sample mean is unbiased for mu, and it really is one line.
Watch. The expected value of x bar is the expected value of the sum of the x's over m. Expectation slides across the sum. That's linearity. So it's 1 over m times the sum of each e of xi. Each observation has mean mu, so that's 1 over m times m mu, which is just mu.
So e of x bar is exactly mu. The sample mean is unbiased. Averaged over all the samples you could draw, it lands dead on the population mean.
And notice what we leaned on. Only linearity of expectation. The expected value of a sum is the sum of expected values. We never assumed the data were normal or anything fancy. This works for any population that has a mean. That's why x bar is the workhorse.
The sample proportion comes along almost for free, doesn't it?
Basically, yes, because a proportion is secretly a mean. Code each trial as 1 for success, 0 for failure, Bernoulli. The expected value of each is p. And the sample proportion, p hat, is just the average of those zeros and ones.
So it's the exact same argument as x bar. E of p hat is 1 over m times mp, which is p, unbiased.
And this is why p hat sits at the center of that proportion confidence interval from lecture 15. P hat plus or minus c times the standard error, as long as the sample's big enough. NP hat and NQ hat both at least 5. The central limit theorem standardizes p hat into a z, and it's the unbiasedness that keeps the interval honestly centered.
Now, the one everybody trips over, the sample variance, s squared. The formula is 1 over m minus 1 times the sum of squared deviations from x bar.
And it's unbiased. E of s squared is exactly sigma squared.
You can show it in a couple of lines. There's a tidy identity that splits the sum of squared deviations, and when you take expectations, the whole thing collapses to m minus 1 times sigma squared. Divide by m minus 1, the m minus 1 cancels, and you're left with sigma squared, exactly.
But here's the intuition, which is the part worth keeping. We measure deviations from x bar, not from the true mu, and x bar is pulled toward our own data, so those squared deviations come out a touch too small. Divide by m and you'd underestimate sigma squared on average, biased low. Dividing by m minus 1, 1 degree of freedom spent estimating mu, bumps it up by exactly the right amount. Now, a plot twist. Squared is unbiased for sigma squared, so s, just the square root of s squared, must be unbiased for sigma, right?
That's the trap, and the answer is no. Taking a square root is a curved operation, nonlinear, and expectation does not slide through curves the way it slides through sums. So E of s is not the square root of E of s squared.
Which means E of s isn't sigma. S actually tends to underestimate sigma a little. The good news, that bias shrinks as the sample grows, so for big samples it's negligible.
And here's the rule of thumb to carry out of this whole episode. Expectation passes cleanly through straight line steps, odding, scaling. It does not pass through curved steps, square roots, squaring, reciprocals. That single fact is exactly why x bar, p hat, and s squared stay unbiased, while s slips.
So far, we've got one yardstick, unbiased or not, but often several estimators are unbiased. How do we break the tie?
With efficiency. If two estimators are both unbiased for theta, the one with the smaller variance, the tighter sampling distribution, is the more efficient one.
And among all the unbiased estimators of theta, the single tightest one earns the title most efficient. Look at the picture. Theta 1 and theta 2 are both centered on theta, both unbiased. But theta 1 is narrow and tall, so it's more efficient. Theta 3 is off to the side, biased, out of the running entirely.
And this finally settles the mean versus median question from earlier. For a normal population, both the sample mean and the sample median are unbiased for mu, but the mean has the smaller variance, so x bar is more efficient, and that's why it's our default. The median was unbiased too, it just wobbles more. Last move, and it's the bridge back to lecture 14. Even the best, most efficient unbiased estimator won't hit theta exactly on a given sample.
So instead of pretending one number is the truth, we report a range, a lower bound and an upper bound, with theta somewhere inside. The endpoints come from the estimator and its sampling distribution, and the length of that range tells you how accurate you are. Tighter is better. A bigger sample shrinks the variance of x bar, sigma squared over m, so the interval shrinks too.
And because each sample gives different endpoints, the endpoints themselves are random. We choose them so the probability they straddle theta is 1 minus alpha. That range is the 100 times 1 minus alpha % confidence interval, the exact object lecture 14 built. Concretely,
A sample of SAT verbal scores might hand you the interval 530 to 550 for the true class average. Those endpoints came from x bar and the sampling distribution of x bar, and the width is the accuracy reported honestly.
Let's tie it off. An estimator is a random rule. An estimate is the one number it gives on your sample. Unbiased means E of big theta equals theta. And x bar, p hat, and s squared all clear that bar. S squared thanks to the n minus 1. S itself is biased. And when several are unbiased, you pick the most efficient, the tightest.
And why care? A confidence interval is just a point estimate plus or minus a margin. Because x bar, p hat, and s squared are unbiased, the estimate isn't systematically off, so the interval sits honestly centered on theta. Bias would slide the whole interval sideways.
It all connects. Lecture 14 built x bar plus or minus z times sigma over root m around the unbiased x bar. Lecture 15 uses the unbiased p hat for proportions and s for the t interval. Point estimators are the backbone of every confidence interval. That's Walpole 9.3. See you in the next one.